has anybody read a geotechnical report? Impressed. It wasn't because you were suffering from insomnia?
Right.
There was no medical diagnosis associated with that? So that's good.
Assignment.
Do what?
It was a homework assignment we had.
It was a homework assignment. Well, there are worse homework assignments. If your instructor ever tells you to read an ASTM standard, that's perhaps the only thing worse than reading a geotechnical report in terms of its ability to bore you. And there's a lot of information contained in one of these. And depending upon where you are in the construction project, whether you're on the design side or the construction side or the structural side versus the architectural side, or maybe a utilities contractor versus an earthwork contractor versus the GC, each of you have a different piece of information to extract out of that report. So that's why it has to be so voluminous, because we have to address everybody's needs on the project. When I first wrote my first geotechnical report, it was less than 2 pages plus the logs. We can't say hi in 2 pages plus the logs these days. Most reports run 30-ish pages in length plus the data that's behind them. I've just reviewing one over lunchtime that is 175 pages in length. And, but very complicated projects. We're going to have 100 feet of elevation change inside of the footprint of the buildings that we're working on. And there's 4 buildings. So when you have those kinds of complicated issues, it takes a lot of information to be able to explain that. So being able to find it efficiently and recognize what it is important. So we'll talk about that. We'll talk about the major pieces of a geotechnical engineering report, where you can find them, understanding some of the information, some of the lingo that's contained in there. If you've read some of that, there's terms that we use. We talk about fat clays and lean clays and Hatterberg limits and Proctors, and for some, for the newer people in this field, that would be a strange piece of lingo. And then who cares, really? I mean, obviously me, because it funds some of my bad habits. I'm a huge car guy and have lots of, spent most of my spare income during the course of my career building cars. And we'll probably have to continue well past my normal retirement age because of that habit, but that's okay. So besides me, who cares? For some, it's just to check the box. For, some cities require that we have a geotechnical report, right? Because they won't give you a permit without it. That's probably not using it to its fullest potential. Architects need it to do some of their design stuff. They don't use it as fully as some do. Owners like to know that they're sometimes buying a site that's suitable for their building. We had a site recently that we investigated for a client, and when we told him that he would probably see 2.5 to 3 feet of settlement based on the grading plan that he had and the weight of his building, he decided not to buy it. That was probably a good call. That's probably outside of the normal tolerances for cracking drywall and other finish issues that go on with that. Contractors, certainly every contractor that ever walks onto the site should understand and recognize the importance of a geotechnical report. Banks sometimes require them. The subs frequently do, particularly if they're the ones playing in the dirt. The utility guys, the electricians, the plumbers, foundation contractors, those kinds of folks. And then the structural engineers and the civil engineers are probably the guys that use it the most. They dig into the details. They're looking at what the materials are for grading. They're looking at what the materials are for foundation requirements and capacities. And they're the ones that want to get the most out of it. So why do they care? What happens if you don't have one? Sometimes bad things happen, right? It's money and risk. And the more you get involved in the construction projects and the longer you get involved in the construction projects, those are the underlying drivers for most of the decisions that we make. We don't want to expose ourselves or our firms to undue risk, and ultimately risk is really a function of money, right? If we take a risk and it ends up badly, it's going to cost us something. And nothing ever goes bad, soil-wise, right? Everything always performs like it's supposed to. I often tell people that my objective as a geotechnical engineer is to never hear from you after the project is done. That's my goal. And furthermore, I want to help you as a construction and design team to make sure that your project never ends up on the 10 o'clock news. It can be on the 6 o'clock news. The 6 o'clock news is good, because the 6 o'clock news is all the ribbon cuttings and the baby kissing and all the wonderful things that go on in life, because no one's there to see it. But all of the tragedies, the fires, the collapses, the death, the mayhem, the murders, the robberies, all that stuff ends up on the 10 o'clock news, and we don't ever want our projects to end up on the 10 o'clock news. I'm perfectly content if the only people that see the stuff that happens on the 6 o'clock news are a much smaller group of people, because that means it was a good thing, not bad. But we have slope failures, we have wall failures, we have sinkholes. Sometimes we have buildings that slide down a hill. And believe me, in 35 years of doing this, I've seen, I won't say it all, because that would be a pretty pretentious statement, but I've seen most of the problems that can happen, and they're not good. If the geotechnical engineer screws it up, it's expensive to fix. It really is expensive to fix. Because now we've got a building sitting on it, the building's typically in service, and things start moving around, it's not good. I got the displeasure one day, about 15 years ago, of standing in a backyard of a gentleman who had built his house out on the edge of a slope without the counsel of a geotechnical engineer, and after some pretty horrific rain events, his house started to take off down the hill. And I had the displeasure of sharing with him that his $350,000 house was probably going to cost him $500,000 to maybe fix it. And that's not a good place to be. You don't want to be there. So we try not to do that. So when we go out, we use a whole bunch of different tools in our toolbox to go out and peer into the subsurface soil conditions. We don't have X-ray vision. I wish I did. I could probably make a lot more money if I did. But we're trying to sample on some kind of an intelligent interval the soil conditions that are there to bring back a representation of what the site is and how it's going to be impacted by the proposed construction. So the level of investigation that we do for a 5,000 square foot Subway sandwich shop on a virgin site that's never been touched other than perhaps for farming is different than what we do for a multi-story, million square foot high-rise office building. That make sense? Yes?
In the event that you did a geotech report and didn't find a condition that eventually led to a building movement that was going to cost an owner a bunch of money, is the geotech engineer on the line for any of that?
Well, it depends. Potentially. And the reason I say that is because we frequently investigate things and give clients recommendations, and they don't follow them. And at that point, you're on your own, buddy. If we did something negligent, then yes, we would. It's a very high-risk business. And it's important that as consumers of that you understand what those risks are. And the whole point of this is to help you be better consumers of that information. Understanding what the risks are, because if the building goes bad, typically they just drag everybody into the lawsuit and let the lawyers figure it out. And that's a very unproductive mechanism, but that seems to be how our construction industry is kind of oriented, because the issues are complicated. So we want to find out what the profile is, if there's bad soils there, good soils there? Is rock in our way? Is rock not going to be in our way? Generally speaking, if you want rock to be there, it won't be. If you need rock, if you don't want rock to be there, it will be very shallow. That just seems to be kind of how Mother Nature works. It is also important to understand that all of the easy sites are the ones that are ahead of us. Because we skipped over the tough sites. If you have a choice of 2 sites, and for the last 100 years or so, we've had a choice of plenty of cheap and easy good sites, why would we pick the tough one? Why would we pick the one that has a lot of grade change? Why would we pick the one that has a lot of soft soils or hard rock or those kind of things, when the one next door is the same demographic, right? But it's easier. So what's left, as we look around major metropolitan areas, what's left is typically the tougher stuff. I did a project about 10 years ago that had 1 million square feet of face of retaining wall. Get your head around that. 5,600 lineal feet of retaining wall that averages 30 feet in height. And the reason for that is because the owner that was developing it was a retail developer, and he wanted 2% slopes on his parking lot. And there was 195 feet of elevation change between one end of the site and the other. But it was surrounded by dense, single-family homes that were older, and it was a home redevelopment, Home Depot-ish kind of place, and he wanted to be close to those rooftops. So he spent $4.5 million on retaining walls. We didn't build on that site for decades before that, because it didn't make any sense. So now we do. And then after that, we're going to provide some recommendations based on what the project needs are. You know, is there going to be paving? Is there going to be foundations, slopes, retaining walls? Is there old ponds that we need to deal with? Is there any other unusual things that are going to cause the project problems? And one of the things that if you leave here with no other piece of information is this. If you are given a geotechnical report, or you see a geotechnical report for a project that you're working on, open it up. In the first page or 2, there will be a project description in there. If that doesn't accurately describe what you're building, your hand needs to go up. Because geotechnical engineering recommendations are very specific. They're very specific to what it is that's being placed on the site and the circumstances under which they're being put there. For example, if you go into northern Kansas, southern Nebraska, and you design a building with a slab on grade foundation, you will get a very FAST recommendation. But if you put a basement in that, don't change anything else, don't change the footprint, don't change the elevation of the finished floor, don't change anything else. You just put a basement in that, you will induce an extra 1 to 2 inches of settlement. And if you didn't ask somebody about that, you just bought that risk. Perhaps unwittingly, but you just bought that risk because you did something that was outside of the scope of the geotechnical investigation. It's really, really important that you understand that those 2 things have to match up. You wouldn't take someone else's drawings, you wouldn't take a set of drawings from a project in Texas and try to build them here in Wichita. There's a whole bunch of different code issues that's going on. Same is true with the geotechnical report. It's very specific to what's being built, what the finished floors are, what the loads are. Everything about that is unique, and you need to make sure that that represents what you're actually building. I can give you a couple of dozen examples of some really bad failures that have occurred because people did that. And back post-recession, go back 10 years, 2008, 2009, we started to recover in 10 and 11. There were a lot of sites that had investigations that were done on them pre-crash, pre-recession, and a lot of those developers, when either sold the lots, they went into foreclosure, property changed hands, a lot of property changed hands, and someone else picked it up for pennies on the dollar from the bank. And some of that came with maybe a phase one, might have came with a little bit of a topographical survey that someone had done, and may have come with a geotechnical report for whatever it was that was being designed for before the recession. And they say, here's that. It goes with, it's just part of the due diligence and goes with the report. And a good number of that was retail, because we were building retail like crazy in 2008, and it stopped all of a sudden. And so there was a number of projects where, a contractor or an architect or an engineer was handed a geotechnical report and said, here, just use this. And it didn't match the project anymore because we weren't building retail anymore. We stopped building retail for the most part. And we had a number of projects that almost blew up on books. So, in order for us to do our work, we have to know some stuff. We have to know some stuff about the project in order to give you the right recommendations. We can go out and drill holes all day long. We're happy to drill holes all day long. I have in my personal library probably something on the order of 40,000 borings that I've looked at. I've worked on north of 28,000 projects during the course of my career. I've done lots of stuff. So we kind of know what's supposed to be there. What gets us all in trouble and why we do most of the investigation is because of the stuff that we don't know. Stuff that's not supposed to be there. You ever dug a hole in your yard? Did post holes? Were you surprised when you hit something? Because you didn't know what was there. And even when we do a good investigation, there's an opportunity for us to not know everything, but at least we get some idea what's going on. So we need to know what the building is. What's the shape of the building? How tall is it? How heavy is it? How much does it weigh? And how are we transferring the weight of that building to the soil? Geotechnical engineering is an applied science. It's not structural engineering. Structural engineering, we use 30,000 KSI steel, 60,000 KSI steel, 4,000 PSI concrete. Those are very well-defined properties. Mother Nature wasn't that kind to us. It varies quite a little bit across the course of the project site. So we need to know how that's going to be transferred. Do you already have a foundation plan? Do you plan to put the building on drill piers, spread foundation? If you already have a pre-thought process of what that is, communicate that to us. Cuts and fills. Where are you going to place fill? Where are you going to take the cut from? In the project I was telling you about earlier that had 120 feet of elevation change, the weight, you take 65 feet off of the top of a hill and you put it on the other side of down in the valley, you have two things that's going to happen. One is where you take 60 feet of fill off, that soil is actually going to relax and rise up. And then you put it on the other side, and it's going to compress the soil that's underneath that 60 feet of weight. Soil weighs 135 to 140 pounds wet density. So 60 feet of that is 9,000 PSI. That's significant. Don't check my math. I got wrong about that. But it's probably more than the building. It's probably significantly more than the weight of the building. So that makes a difference. I've got a project I'm working on right now that the entire schedule for the entire development, and it's a 275 acre development that's got almost 2 million square feet on it, is driven by the settlement caused by the deep fills. Everything the contractor does has to be sequenced in such a way that we make sure that the new fill that we placed has consolidated the softer soils underneath them in such a way that the building performance will be acceptable. So it matters. What are you doing about traffic? And then lastly, and this is a piece that we rarely get the opportunity to know in advance, is what's the construction schedule? Because it makes a difference whether you build something in August in the Midwest or whether you build something in December. There's some tricks that you need to be aware of. There's some things that you have to take into consideration depending upon what time of year it is in this part of the country. In some parts, in Phoenix, doesn't matter. It's hot all the time. We're not hot all the time. We go through long periods of wet weather, followed by long periods of hot weather, followed by long periods of cold weather, and a couple of 3 nice days in there. That if you're a golfer, you want to go out and try to golf, right? So there's a bunch of testing that we do that's inside the body of the report. I won't get into this in any real great detail, but all of these tests are oriented around measuring the physical properties of the soil so that we can apply that to your project. So we want to know things about strength of the material, consolidation of the material. Is it going to swell? Is it going to, how do we compact it? How is it going to support different types of loading conditions? And all of that is oriented around making your building perform the way we want to. Every building has a different set of performance criteria. If you build a masonry building, it typically can take less stress, less movement than a stick frame wood building will. Just less flexibility there. We do a lot of work for grain bins and water towers. Water towers can take huge settlements, and as a result, they can have higher bearing capacities. The same soil that we would give you a 2,500 PSF bearing capacity for a single-story structure, we might give a grain bin 8,000 or 9,000 PSF bearing capacity for. But guess what? The grain bin is going to settle a foot. We hope it goes like this. Because we don't ever want to be part of the leaning tower of grain, right? We've got the biggest ball of yarn in Kansas, the biggest ball of string. We don't need a leaning tower of grain on top of that. So it matters, but we don't have ADA issues in a grain bin. We don't have electrical connections in a grain bin. We don't have plumbing connections with a grain bin. So we don't care. We want it to be as efficient as it can be. Has anybody been to Italy, seen the Leaning Tower of Pisa? It's kind of cool. I got the opportunity to go there about 4 or 5 years ago when my son studied abroad for a semester. That was the only excuse I thought I could ever come up with to go to Italy. And it was interesting that the building is actually curved. You can't see it in any of the photographs. None of the photographs I've ever seen show you this. But it was very much manual construction back in the 1800s or 1700s when it was built. I'm not a history buff, so don't quote me on any of those days. But they were fixing the building because they built it with plumb bobs. It's masonry construction, stone construction, and they were working with plumb bobs. And you can tell that they were fixing it. It had started to settle before they ever got past the first floor. And they were fixing it. Because you can see just an ever so slight curve on the base, the lower 3 levels of the building. And after that, it kind of straightens out. So it must have slowed down or they got faster or something. But it started moving before they got the first floor of that building done. And the masons were fixing it. Because they just kept running a plumb bob. Plumb bob didn't care what was going on underneath it. You put every piece up level and you think it's going to be okay. It's interesting. If you ever get to Italy, look closely at that because you'll see it. That's probably the most famous settlement problem on the planet, I think. I'm not 100% sure about that, but it's certainly one that's gotten more press. So when we get ready to do that, we get all that lab testing done, and then we're going to put together this report talking about the project, talking about the lab data. We love talking about lab data. We're engineers, you know, we're total geeks about some of that kind of stuff. And then we write a report. It has to be reviewed by somebody else before you guys ever get the chance to see it. But it's important that you know what those steps are. It's difficult to do that in less than a month. 3 weeks is a real stretch. You got utilities that got to get called in before you can drill it. You got a couple of days in the field to do field work. The lab testing takes a week. You got to analyze it. You got another week to get a report done, get some review done on it, get comments back from the design team. So it's a month from start to finish, roughly. I had a client today call me and wanted to know if I could give him a report next Thursday.
So I'm guessing when a client calls you to have you guys come out and do borings and initiate the report, ask for a quote, do you ever get pushback from clients on like they ask you to do less borings than maybe you would have liked to have done to help control the cost of that, or do people generally go with your recommendations and fight that much?
Not often. Sometimes we'll see architects that will give us a site plan and they'll put boring locations on them, and sometimes those will be light. But they usually if we call them and say, hey, look, this looks a little skinny and here's why, usually we don't have a great deal of difficulty with that. And sometimes they say, bid the base scope, tell us why you want the others, and include that. There's certainly more risk with less information, yeah, for sure. Typically, we do, a good rule of thumb on a bigger site is a boring for every 7,000 square feet. Obviously on a small site that doesn't apply, but if you get up in the 50 or 60,000 square foot site, you can get a boring for every 10,000 square feet. And if you do that, that's sampling at about a 1 part per million. You get bigger than that, you start talking about 1 part per billion, you know, then you're really not getting enough information to be able, because you've got a, you know, 5.5 or 6 inch diameter sample out of 10,000 square feet. That's what you're looking at. So we're counting on some of the expertise that we have, some of the project experience that we know from the area. Geotechnical engineering is a very regionalized practice. I practice, 90% of my practice is Kansas, Missouri, Iowa, Nebraska, and a little bit up in the Minnesota and the Dakotas. I would never touch a project in Texas, or Arkansas, or Louisiana. There's just too many other things. I can get you the guy, because we're a big company, we have lots of offices all over the place. We have a guy there, but it ain't me. There's just too many local practices that are going on that if you mess those up, you're in trouble. Here, in Wichita, we talk about swell potential based on expansive soils in inches. Typically, 1.5 to 2.5 inches of swell potential is the range of the expansive soils that we have here. Between Dallas and Houston, they talk about swell potential in feet. That's a whole different thing. You know? And I don't want anything to do with that because that's not what I practice every day. Louisiana, or Memphis, which is just south of Missouri, which is a place that I've practiced in a lot. Most of this part of the world, we've got rock that's 50 feet or less. A lot of places it's 20 feet or less. In Memphis, it's in 2,000 feet. Memphis is a big bowl of jello. That's why when the New Madrid fault goes off, Memphis goes away. Just goes away. If you have investment property in Memphis, you might want to rethink that. It's essentially a big waterbed with stick-built stuff standing on it, and when the New Madrid fault goes off, it's going to be the fat kid jumping on the corner. It's not going to end well. Here, we're in pretty good shape. Rock's nice and shallow. We don't have that big wave effect that's going to go on. So we can take a pretty good hit here in the Midwest, in this part of the country, and not get hurt. So we're going to talk about all these different things that are in the site. What we found, where we found it, did we hit anomalies? Were all the borings the same? In some cases they are. we get sites that are very uniform on occasion. We're pretty lucky in this part of the country in that originally all of the rock was deposited by the same geologic phenomena, i.e. a lake. Kansas was an inland lake. So all the rock deposits that we see, certainly for any of our construction, are all sedimentary rocks. And what's that mean? That means that they were all laid horizontally, because they were all deposited by water movement, right? So they all settled out in the bottom of the lake. Different courses over different years, but initially all of those rock deposits were level. So typically we find rock at a very similar elevation, assuming that it didn't weather away during one of the periods of time when it was exposed. The surface of the rock is typically, I don't know, 275 to 600,000 years old, plus or minus a week. I'm not, we're pretty insignificant in that period of time. So we have to understand what it is we're talking about. And a lot of weathering is taking place. One of the things that drives construction projects crazy is the top of rock elevation, because it will vary because of the weathering activities, and where the rock is gone is where the rock was soft. The hard stuff stays. The hard stuff weathers. So if you look around an area and you see a ridge going up that's supporting a hill or something, that was the harder rock because it did not weather away. Are any of you familiar with the Devil's Tower out in Wyoming? The Devil's Tower is a column of volcanic material that is really, really hard, and all the rest of the plains weathered away from it. Leaving a really cool thing. Even if you're not a rock guy, it's cool. So, site plans, we want to look at the site plan. That would probably be included in the report if it was given to us. Aerial photos, we like looking at old pictures, seeing if there was other properties there on the site. That gives us insight to what we got. We also look at old USGS maps, mining history, things like that. Figuring out where we can put borings, what we're going to do. When we go out with our drill rigs and sample that, we like to have a pretty good idea of how deep we're going and what we might find. We always try to take a couple of extra bullets in our gun, just in case we find some stuff that's not exactly what we anticipated. I had a project I worked on just last, I guess it's been 2 weeks ago now, where everything was fine until we got down about 45 feet to the ground, and we hit 20 feet of essentially peat moss. It was so soft that it would not even support the weight of our tooling. So when we rested our tooling on it for our drill stem, it would just slowly sink into the ground. That's not good. That's not good. We run the laboratory testing on the samples. Most parts of the country use an SPT test, which is a standard penetration test, where we just drive a cone into the soil with a given energy and a given distance. We present that data. We talk about where we find the different materials as we go through them. The soils are typically striated across the site, changes in depth over time. Sometimes the good stuff is at the surface, sometimes the good stuff is down farther, just depending on where you are and what you're doing. If you don't need high capacities, a lot of times you don't need that, but a lot of times you do. So, figuring out bearing capacities. Got a trick question for especially you students in the room. Is bearing capacity measurable? Do you have soil mechanics class?
To an extent.
Do what?
To an extent.
To an extent. Is that like being a little pregnant?
Yeah.
I'm just being funny.
I know.
Bearing capacity is not a measurable entity. It's the thing that most people are looking for out of their geotechnical report. I literally handed owners and architects and structural engineers, geotechnical report, and watched them flip through the first 8 pages to the one that says foundation and recommendation. They look at that, look at the number, and flip it close. Those are not my most rewarding days as a practicing geotechnical engineer, I have to tell you. But it does happen. It's not a measurable, and it's certainly not a field measurable capacity. So we can't, if you dig an excavation, you dig a hole in the ground, and call your geotechnical engineer out and say, come measure the bearing capacity of my footing, he can't do that. He may bring a piece of equipment with him, and he may poke it in the ground, and he may tell you something, but he is not telling you the bearing capacity. He's probably measuring the shear strength of the soil in that shallow zone that he's poked into with whatever tool du jour. And if you ask 10 geotechnical engineers what their tool of the day is to do that, you'll get 11 different answers. Yes?
Good question. Very recently I called a geotechnical company. They brought LWD,
Oh, what?
lightweight deflectometer,
Oh, yeah.
which they brought 2 of them, but one of them can measure the CBR
Oh, yeah.
and of course the DCP and all that. So now when you tell me you can call the geotechnical, they cannot measure, what were they doing? I'm
Well,
asking myself a question.
So what should happen is you have a geotechnical report done prior to the start of construction. And then that same company or a similar company comes out during construction and looks at your foundation excavation and verifies that what you have exposed is the same as what was in the geotechnical report. You look up the International Building Code, Chapter 17, Special Inspections, they specifically call that service out, verification of foundation bearing capacities, and by code, you're supposed to have a geotechnical investigation performed prior to that. So you can have somebody come out and verify that the field properties, and typically we measure shear strength. Shear strength is one of the pieces that goes into the bearing capacity calculation. But we'll measure that and verify that that aligns itself with the project design criteria. But you can't start there. We determine bearing capacity and do some of our shear strength testing in a laboratory on a piece of equipment that's about $25,000. It's computer run, it's got all kinds of data inputs, and the device that we bring out to the field is about $250. You don't get the same level of information with that. But it's a good tool to be able to verify. Mostly we can validate that the soils that we see match up with what was called for in the geotechnical report, and everything's good. So that's probably what they're doing.
Well, I'm a little confused right now because on the geotechnical report, we didn't mix cement. It was just a virgin soil. So they gave me the bearing capacity. And then they brought the DCP, they brought the lightweight deflectometer test, and after mixing with the cement, they gave me a new bearing capacity. So it's not on the same material. These are 2 different materials.
Yeah. I don't know, I'd have to look at what they were trying to accomplish. Because we do different things with amendments, soil amendments. Fly ash is one, cement is one, lime is one, kiln dust is one. Every region has a different set of products that they use, and they're almost all cost driven. Typically by the cost of the haul. Whichever's closest, we figure out a way to use most efficiently. Typically in this area, it's mostly been fly ash, but the fly ash, the Class C fly ash that we have is getting in short supply, so we've started using more cement. And we don't have as much history with cement as we do with fly ash, so we're all still playing around with what the optimum mix is. And maybe they were doing something with that, trying to validate that in the field. So all of those things, the bearing capacity is one of the things that we provide in that report, and it's important, but it's not the end all be all. If you're involved in retaining wall design or construction, there are slope stability concerns and global stability and lateral earth pressures that need to be taken into consideration. Most projects do retaining walls on a design-build basis. So the civil engineer will draw a line on a drawing and said, retaining wall by others. And the general contractor typically has to hire somebody to design and price and then subsequently install the retaining wall. That's a pretty common practice for that. But be careful that retaining walls need to have, in addition to the wall design itself, they need to have a global stability analysis done on them, particularly if they're over 5 or 6 feet in height. Usually under 5 feet, it's not a requirement. Certainly anything over 10 feet should have a global stability analysis done on it. And most of the guys that are doing that aren't. They can do the wall design independent of the global stability analysis, and probably 50 or 60% of the wall failures that we see are due to global stability issues, not because the wall design itself is bad. The wall can literally, the whole retaining wall, whether it's an MSE wall or a gravity wall or a reinforced concrete wall, the whole thing can move down the hill and stay intact. And the wall design was fine, but the global stability analysis was not. So keep that in mind in your contracting for those, because it kind of falls in a gap. So the civil engineer said, hey, Mr. GC, it's yours. The GC hands it off to their sub, design build sub, and says, here, this is your piece. And they typically, the wall designers typically put a note in there that says, this does not include global stability analysis. So when the wall fails due to global stability failure, whose is it? For the lawyers to figure out, and you're all going to lose. Everybody's going to lose because everybody's going to get drug into the fight. If the lawyers get invited, we all lose. Everybody that's associated with the project just became a loser. Some are bigger losers than others, but we're all losers. Because none of us are making enough money on our projects to support an attorney for any length of time. So that's what we're trying to prevent, is making sure that that we don't get those kind of problems. We ask most of our clients, we ask them to give us a set of final drawings so that we can review them and make sure that they have interpreted this multi-page document that we gave them appropriately for what they ended up doing. It also gives us a chance to look at it and make sure they haven't changed something. And we probably get less than 5% of our clients that do that. Most of it's, they say, scheduling, we're trying to get it out on the street for construction, get it built, all that kind of stuff. But the faster we go through some of those steps without having some of the quality control, the more opportunity there is for risk. All right, so we're going to give you recommendations for all sorts of types of construction inside of that report. I'm going to give you, what the subsurface conditions are, where water is are you likely to encounter that during your excavation? How do you handle it? How do you handle water that's bleeding in your site? Depends on how much water there is, right? A little water, you build a little trench off to the side and funnel it into it and redirect it away from the site. But if you're doing that in sand, you got a 70-foot hole in sand, which you certainly can on the west part of Wichita, you're going to have a big water problem. And if you don't deal with that, don't build that cost into your bid, if you're bidding a project, you're gonna be in trouble. About 15 years ago, I worked on a new strategic command center in Omaha, Nebraska for Offutt Air Force Base. And it was 12 stories below grade. 12 stories below grade. Water was at, I believe, 12 feet. And they were building one of the most secure Army control facilities in the world, 1,000 feet away from the river. Insane. There was going to be $1 billion construction project, and almost $2.5 million of that was just figuring out how to dig the hole and keep it dry. So there was a double liner system and monitoring that would happen inside. I mean, this has all of the NORAD defense systems that controls the Air Force everywhere in the world in the event of a nuclear attack. It's kind of what stuff. And they decided to build it next to a river. Not sure I necessarily follow that logic completely, but hey, what do I know? I'm just a geotech guy. But those kind of things matter, and sometimes we get in a hurry and don't pay attention to them. Other types of construction that might show up on the site that we know about get brought into that conversation as well. If there's unusual features, a deep well for elevator pits. Elevator pits sometimes get overlooked. Is there a swimming pool? Is there something unusual going on? We'll typically address that with specifics. And then in the back of the report is this boring log. This is the best information. This is a summary document of all of the data that we found on this project site. We have information about the soils, we have information about water levels, all of our lab testing is summarized on this document, and this is the one piece of information that doesn't change. This is data. This is just data. There's no recommendations on this. This can transfer from project to project, but the recommendations can't. But this can. So look at this closely. There's information here on strength parameters, depths, how deep stuff is. This is a relative strength data, so you can just visually tell that this is stronger than this material, and then it gets soft again, and then it gets stiffer again, and keeps getting stiffer with depth. Talk about soil descriptions. Were the holes dry, depth to water? At what point did we measure them with water? What the date was that it was drilled?
So is there a certain amount of time where, the data from these boring logs would become so old that you'd want to do new ones?
Well, you may want to do new ones, because what you don't know is what's changed.
Yeah.
We use old boring log data frequently as a point of reference. It's kind of like a reference lab, a historical document. But because we don't know what's changed between when we did this and when the new project is going on. Sometimes this is our data, sometimes it's someone else's data.
Is there a fairly free information sharing that goes on between different geotechnical firms?
Oh, I would never share mine. And I'm sure they would never share theirs. But it's, if I have their old report, when I issue a report for a project, it becomes part of the construction documents. And if an owner is good, he'll keep that along with the record drawings and any of that other stuff. So frequently I get to see other people's stuff, and I'm sure they get to see mine. I share some of the information, not physically share it with clients if they ask, what can I expect here? Getting ready to build at 12th and Douglas, what have you got in the area? And I'll look and tell them what that information was. I can't physically give them those documents without somebody's permission, because they were contractually paid for by somebody else. But that information is huge in terms of understanding what's there. And I would encourage all of you to look at those and see where it is. The water level, what I did here.
There's no centralized database like some type of GIS system where people are
No.
recording all these borings across all these cities.
No, I keep those 20,000 borings I told you about. We keep those in a GPS located database for our own use, but we don't have any way to, and we probably wouldn't do it anyway, to share that with anybody. But it's a great reference to be able to go back and look at. That's the only good thing about getting old in this business is you remember all that stuff.
But don't you think maybe that's the good thing to do, because as the way he asked the question, there was one project I first heard recently in Texas, and the geotechnical report came out, everything is good, clay soil, none of that geotechnical report mentioned the sulfate in the soil. Here we go, boom, mixed with the cement. My blade man starts saying, according to my grade, I hit the grade, but after a couple hours, the thing is almost 1 inch. I need to go and cut 1 inch. Well, wow. And there's nowhere to tell. And in that massive project, it was only one location.
Oh, yeah?
See? And then all of a sudden, starting now, they going crazy, we realized, oh, big times.
Yeah.
He was not in there. So don't you think that information could have said, if it becomes like public, I mean, just to say, hey, this area that whatever it is kind of giving some information rather than just everybody is hiding on his own?
Well, we do share that through case histories and through Bears Geologic Society. We do share those problems when we find them. It's very well mapped where certain challenging soil types are in different parts of the country. You know, we know that Memphis is a problem relative to the New Madrid Fault. We know that rock is shallow in this part of the country. We know that the expansive soils exist. And we've got all that stuff mapped out pretty good. Not everybody looks at it because it's some of it you have to dig a little bit. It's like mining activity. We know pretty much where most of the mapped mines are for various minerals, depending upon where they were extracted. We get surprised by some, for sure, but for the most part, we know where all the deep mining is. There's a lot of lead mining down in over by Galena and Joplin and that part of the country, and there have been salt mines around here, and limestone mines around Kansas City, and so we know where a lot of that stuff is. But we certainly get surprised. I had the displeasure of discovering a previously unknown piece of karst topography south of Kansas City. Not long after I moved to Kansas City from Iowa, and we knew that there was some soft rock out there and some weathering that had taken place, and I got a call on Friday afternoon about 5 o'clock, and the contractor, who was also my client, was just completely freaked out because a dump truck had disappeared on his project, literally disappeared. Fully loaded dump truck, when they were placing the low volume change material underneath the building pad, punched through a shallow roof on a solution feature in a rock karst topography. And all it was showing was the very top edge of the bed and about 1.5 foot of a cap. As the whole thing was sitting in the hole. And, or you do one of those classic stand around scratching your head going, well, that's going to be bad. It's Friday at 5 o'clock, and that's not how anybody wanted to end their week or start their weekend. But we didn't know that before that. We had discovered that on projects, and Unfortunately,
Cave system?
what?
Is it part of a cave system?
It wasn't caves, so there's caves, there's karst, and then there's solution featuring, and they're kind of, the only difference between them is a few 100,000 years of time. So it starts off, the rock is soft, and it weathers away, typically closer to the surface, and the rock decays and turns into kind of clayey material. It's not really clayey material, but it's very similar to clayey material, very soft, very high moisture content, and but the void is still full. And it's not until, you know, a significant amount of time goes on beyond that, that then washes away and leaves rock, a cave behind. The difference in karst topography is karst normally happens in softer rock, and the softer rock tends to have sinkholes because the roof isn't strong enough to support the overburden above it. And so then the roof collapses into that void and brings the soil and houses and, in some cases, cars. I'm not sure if you remember the Corvette Museum deal, that the sinkhole that swallowed the Corvettes. I'm a Corvette guy, so I paid very close attention to the $1 million worth of Corvettes that went down in a hole in about an hour and a half, and they had it on tape because it was in the National Corvette Museum in Bowling Green, Kentucky. Look it up if you're a car guy, it breaks your heart. It truly does. To watch all these expensive cars disappear under camera in the middle of the night when they're going down in this hole. But we know where a lot of those areas are, but we don't know where all of them are. All right, so we're getting close to the end here. This is another tool that you'll frequently see in the back of the geotechnical board. It's called a fence diagram, and it just simply lines up all the boring logs. And one of the things that we like to do with this visually to help people understand that is to put this dark line here, this black line here, is a proposed finished floor slab, as we know it when we issue the report. So we can pictorially show you what you're going to have to be excavating and what you're likely to be sitting on from a bearing capacity standpoint on your site. So it's a really good tool. Not everybody does it. We probably don't do it on every project, but certainly if there's a significant change in materials, significant changes across the site, we like it. It helps us, so we know it helps. It's got to help everybody else. It helps us to visually picture what's going to happen on a site when we put that in there, and make some recommendations about what the materials are going to be. So what about the other stuff? What about questions that you have? You got a geotechnical report and you don't understand it. Call the engineer. Call the guy that wrote it. If they won't answer your questions about their report on project you're working on, you've got the wrong guy. If you've got a solution or an alternate that you want to use, call it. Ask him. There is no one answer. There's one thing I've learned in 35 years of doing this, there is always choices. Now, some are less desirable than others, to be sure. We could put everything on drilled piers, right? Make the geotechnical engineers happy, but the owners wouldn't be able to afford to build in. So that's not really good for the construction industry as a whole. But there are always choices, and contractors in particularly frequently pay more attention to some of the cutting-edge technologies and are willing to invest in them. And your geotechnical engineer should be willing to listen to that. If the science works, then it ought to be a viable option that we can at least talk about. Pros and cons, everything has pros and cons associated with it. If there's a local practice, if we recently, for decades, we have used Class C fly ash as a soil amendment. And in the last, Class C fly ash was generated by burning Western coal in a fluidized bed power generation plant. What everything was here in the Midwest, because it was all designed by Burns McDonnell. Burns McDonnell designed 90% of the power plants, so they designed them all the same. And they all got their coal from the same place because the eastern coal required some other exhaust emission kind of crap. So we had this great supply of of Class C fly ash. Well, they've started to retrofit a bunch of those power plants, so the supply is going down. And the ready-mix industry has always been a big consumer of Class C fly ash, and they're sucking up a lot of that fly ash. So now we have to find a different material. So the economics start to play into that. We're talking about cement, and we're talking about lime, and we're talking about some other products, trying to find the best, most economical solution to accomplish what we need to have happen. What we want is to make the buildings perform like we expect them to. And we want to help you to do that as cost effectively as we can. So if you've got a good idea, ask. We'll listen to it. All right, and then I know that everybody, come to this, everybody probably has one burning question that they always wanted to ask a geotechnical engineer, but we're afraid to, right? Is that nobody ever, I bet I've interviewed 10,000 students during the course of my career at PSI and previous employers, and I've yet to find a single student that told me that I always wanted to grow up and be a geotechnical engineer. Firemen, contractors, policemen, all teachers, all kinds of stuff have been on that always wanted to be list, and never as a geotechnical engineer. And I have to admit that it wasn't on my list either when I entered college. So, questions? Did I help? Yes.
If you have to pick, either modify the soil with lime, and I know there's a lot to get to that decision making, whether should I go with the lime or cement. But let's take all the, let's say the sulfate content out. It's just a high clay soil versus sand kind of soil, less PI, high PI. And then you have these two choices. You have to pick whether to modify that soil with a lime or to modify that soil with a cement. And I attended one of the conferences in Texas, and one speaker saying that there's a research in WDS airport, where it is. They say they took the soil and the lime is leaching out after 10 years. And that soil reverse its property to there's no trace of lime at all. So if you have to make a choice as an engineer, maybe a young engineer, geotechnical engineer, you know the cement is not going to change the product. It's not a chemical reaction, but it's just going to bind the particles.
Right.
Which is the best way?
Well, they both have their drawbacks. For most of our applications, we're trying to prevent swell potential. That's what we use soil amendments for mostly. And lime is more effective than that. But it has to be handled twice. So you have to mix it, let it sit, and then mix it again and compact it. But the beauty of lime is that once it's been mixed and that rotting process has taken place and you reuse it, it's always lime treated because it treats the soil at the molecular level. Whereas if you use cement, if the plumber comes through and digs a plumbing trench through it, you no longer have cement treated soil. You have soil that has cement in it. I mean, if you think about your concrete driveway, it's a pozzolanic material. If you cut a trench through your driveway and take all that aggregate that was ground up and put it back, you no longer have cement. You have aggregates coated in cement, but you no longer have concrete. That's the same thing with fly ash and cement, because they're both glues. They're trying to glue the particles together so they behave better, and once you break those bonds, all bets are off. You have to start all over. So lime is the better product for that particular application, but most of the time it's not economically feasible. The time factor plus the cost of hauling it, because it has to come in a semi-truck from pretty significant, I don't even know where the closest lime source is, I think up in Omaha. When you start trucking something from Omaha, I mean, it gets expensive fast.
And then now in time,
Yeah.
all this stuff.
The DOTs are willing to pay for that. The DOTs and the airports are willing to pay for that because of their investment structure, but most commercial structures, projects can't afford it. And, you know, when there's a better, cheaper alternative, yeah. All right, well, thanks. I've got a business card up there. Do you have a question?